Good morning. It is the 1st of December and we are starting Unit 5 of. So again, what we learned was potential energy is that place where energy is building up and we're waiting to release it. So when is it the greatest? Well, at the very top of the hills. What is kinetic energy? That's great. Yep, kinetic energy is that energy in motion. And then when is it the greatest? Well, we discovered by watching the video that it's greatest at the bottom of the hill because we're having an exchange at one point. So that answers question 5. Is it possible to have both at the same time? Absolutely. It is possible to have both at the same time as where the car and the roller coaster is still coming down the hill and some of it's still at the top. So we have a 50-50. So on that initial drawing here in our first slide, right here, that would be right here at W. So here, and then we're saying down here, so we'd have combos in here. Here would be our greatest at Y, the greatest point of kinetic energy. All right. So here on our digital slide is we did some dragging and dropping. And you're going to want to pause the slide here and make sure you dragged and dropped. What we dragged and dropped over were the labels potential energy and kinetic energy. We're talking about the types of energy that potential is stored in its position. It's not moving. The higher the object is, the more potential energy. So potential energy is increased based on height. I have potential energy if I'm holding the ball at 3 inches at the table, but if I'm holding the ball at 6 feet, it has greater potential energy. And we dragged over the example of the cup sitting on the table and the little picture. Kinetic energy is energy of motion. This is slide 5. And it increases based on motion and mass. So the greater the speed, the greater the kinetic energy. So here, so the greater the mass as well, the greater. So right here's that table with the cup. We move that over. And the example of a cup falling off a table or riding a bike down a hill. So when an object has more potential energy, it has less kinetic. And on the other side, when it has more kinetic, it has less potential. So right here, you're going to use the sentence stems and you're going to answer this. How are potential energy and kinetic energy different and alike? Well, kinetic and potential energy are both alike because they're energy. Potential energy is energy of standing still or stationary, while kinetic energy is energy of motion. So we're here. So question 1, at which point will you find the greatest potential energy? And you're going to put that in, just type it in that box. And at which point can you find the greatest kinetic energy? So I want you to describe what happens here in 3 when the potential energy from D to E. So we're coming back to potential energy and we're going into kinetic. And then I want you to describe the amount using percentages of potential and kinetic energy at point B. And I'm going to wait. You can pause the video here and answer. But one of my friends just said that he believes it's at 50-50 here at B. Yes, because that cart, half of it's over and we still have some up here. So 50-50 is a pretty good answer. Very proud of you. So on a half sheet of paper that I gave you, you're going to draw a short roller coaster track. You're going to spend the next 10 minutes working by yourself or with a neighbor. You're going to label 5 points, A, B, C, D, E. And on the quarter sheet we handed out in class, you will then answer those questions about your roller coaster. Now, if you weren't present, I'm not going to ask you to do this, but I want you to really pay attention to the video and slide number, this slide here in your notebook. Okay? And this is slide 6. So I want you to pay a lot of attention to that. All right. I want you to look at this picture and say what's occurring. That's right. There's 2 guys running a race. How fast do you think they're moving? Okay, so anywhere from 2 to 20 miles. Somebody just said 30 miles per hour. All right, we'll have to see. What is speed? So we're going to talk about what is speed. Okay, yep. All right, those are some good ideas, but let's keep looking. And what are other examples of races? Okay, oh yeah, you said cars. You said bowling balls. You said, all right, animals running, horse races. Very good. All right, so let's look at this. Now this, my friends, is slide number, this is all part of slide number 7. So this is in the upper right-hand corner of the slide. You're going to drag and drop what is missing from your notebook here. So you can pause and you can drag and drop to this corner. Okay, great. But speed describes how fast an object is moving, and that is distance over time. So here's the formula here. Okay, average speed is total distance divided by total time. Yep, and the car speed is 50 miles, so distance, per hour. So in 50, so when you have the distance over the time, we get miles per hour. Okay, this is in the upper right-hand corner, so up over here on your slide 7, and this is velocity. It is speed with direction. So you figure out the speed, okay, so you got this. So that's distance over time, okay, because we want to find speed. And you're going to say the car's velocity is 50 miles an hour east. So we're adding direction, where it's going. Look at the little compass rose here, and there's east circled, so that's telling us the distance. We could say the car is moving up or down if we're talking about a roller coaster, but it has a form of direction to it. All right, so now you're going to watch the speed and velocity. There's a lot of physics, but always remember the difference between speed and velocity is that velocity includes what? And you're going to type your answer here. If you go back, or actually it's right here in slides, in that slide, it includes direction. So yes, as we watch through this. The bottom of slide 7 is speed, velocity, and acceleration. So you're going to drag it, pause here, drag and drop what's on this slide from the left or right side, wherever you have it, can be seen as speed or direction, so a change. The change in direction and slowing down. So the car accelerates when going around the curve. So speeding up, slowing down, changing direction, so the car could turn to the left. That would be a change. Speeding up or slowing down. So you're going to watch for these key words like accelerates, decelerates, changes from east to west or north to south, up or down. We're going to be specific about changing direction here. So I'm accelerating because I'm speeding up. I'm accelerating because I'm slowing down. Here's some views. I'm accelerating because, as you see the bees, changing directions, up, down, loop-de-loop, left, right. So that's kind of a cool picture to remind you of acceleration. Now this is another really cool video about acceleration. So you can sit there and watch it. It's about 4 minutes, and she's really informative. So pay attention to that. And then lastly, on this slide, you're going to answer this question. How can you differentiate between speed and velocity and acceleration? So here are the sentence stems. And the first one is the difference between speed and velocity is that velocity has, you said it, direction. Acceleration represents a, yep, exactly, a change in speed or velocity. So what you're going to do is you're going to drag these over so an airplane slows down as it lands. So you're going to look at that and go, wait a minute, speed, velocity, or acceleration. Okay, I think it's going to be this one. So you're going to drag this over, just drag it over. A bird migrates north for winter at 23 miles an hour. Wait a minute, one has direction and speed. So there's direction north and there's speed, okay? So that's going to be the teal one, so that can go here. And a marble speeds up as the ramp gets steeper. Absolutely. Yeah, okay, let's hold on to that one. A baseball travels 30 miles per hour. That's definitely speed. So we're going to put this here. All right. So as we're doing this, you're going to look at these each and you're going to make a determination. So let's look. A horse galloping 10 miles per hour east. Oh, that's speed. There's my speed, but a direction, velocity. So I'm going to click on that. I'm going to copy it. I'm going to click on, right click on it again. I'm going to hit paste and I'm going to drag this over. So I want you to do your best and try these. Remember. All right. Which one? You've got 9 here. Can just click and do that. Drag those color boxes and you're set to go. Okay. Now in class today, we finished this out. So when you rejoin us, you'll have this and you'll just fill this out. It's a short one. Whether it's speed, velocity, acceleration. If you were here in class, we did that in class. Okay, and then our exit ticket for together was Jupiter's moon, Europa, orbits Jupiter at about 30,700 miles per hour. This is an example of speed, velocity, or acceleration. Well, I have speed, but it orbits, so it's giving me direction. So that would be velocity, because there's no change. So yep, velocity would be the good answer. So remember that when you're talking about like the moon orbits the earth here. Okay. So we're going to talk. So I want you to fill these out, do this together, and we will see you on Friday.